All right. Hopefully this is a good overview and a good transition from what we've been talking about a lot for the past couple days, which is asteroids and small bodies, into the geochemistry breakout session, because I'm going to combine both here and revisit the first science from a spacecraft that was really dedicated to small body research, and that's NEAR. NEAR was long enough ago now that it probably wouldn't hurt to give a brief overview. So NEAR was the first mission in the Discovery program, the first dedicated to studying an asteroid where it orbited, which was the S-type near-Earth asteroid 433 Eros. There were a multitude of orbital altitudes they took, and there was quite a comprehensive payload. But since we'll be talking about the geochemistry, we're going to focus on just a few of these, specifically results from the X-ray and gamma ray spectrometer, and to a lesser degree some of the spectral measurements from the multispectral imager and near-infrared spectrometer. And the other really interesting thing about NEAR is, as depicted in this cartoon here, is that it actually landed on Eros and performed the first in-situ science from an asteroid surface. In particular, after the landing, NASA extended the mission for 2 weeks to allow the gamma ray spectrometer to accumulate some data. And that's the data set that we're going to be talking about primarily here. So as NEAR came in, as you can see in these final 4 descent images, if you can't see, this scale bar is 5 meters, right? So these are some pretty good images here. As it was landing, it was coming in this direction, and it was transitioning from a rockier, sort of typical terrain into this smooth area, which was one of the ponded regolith deposits that were observed all over the surface of Eros. So it's one of the things that we have to think about as we talk about the landing, which is that the measurements were made in this area, which may not be representative of the whole surface. So one of the objectives of the NEAR mission was to connect the composition of these S-type asteroids, which are the most common spectral type near Earth, with the composition of specific meteorite types. In particular, it was long suspected they'd be related to the ordinary chondrites, which are the most common meteorite balls on Earth. And we heard a little bit yesterday from Chris Russell about the power of this, right? He was talking about this geochemical picture that we had developed for the evolution of Vesta. Before Dawn even launched, we had a picture which has largely held true. So much information was gleaned from the analysis of those meteorites that we had this great picture. And the question is, what other meteorites can we do that for? If we can connect Eros, for instance, to a meteorite type, what can we learn about it by having those de facto samples in hand? So shortly after the mission ended, Tim McCoy sort of compiled all the information that we'd learned from the different geochemical measurements to see really where things fell. And I've broken them up here by box. You can see the XRS spectral results and the GRS. By and large, we found that the data sets were consistent with an ordinary chondrite-like composition for Eros. But when you dig a little bit deeper, you find there are some inconsistencies. So for instance, for both XRS and GRS, major element measurements, and we're talking about things like aluminum, calcium, magnesium, they were all consistent with the compositions of the ordinary chondrites. But then look at the XRS results. For instance, the iron to silicon measurement pointed towards an H chondrite-like composition. Measurements of minor elements, chromium, manganese, and nickel, pointed towards L and LL chondrites. So these measurements in and of themselves are inconsistent with each other. Then there's the sulfur measurement, and sulfur was found to be completely depleted on the asteroid relative to the ordinary chondrites. The spectral results, a few different analyses pointed pretty strongly to L and LL chondrites. And then GRS, again, major elements looked a lot like ordinary chondrites, but there was this iron to oxygen measurement, which is highly diagnostic of meteorite type, and it was subchondritic. So there was a pretty complicated picture going in. So I'll come back to this iron to oxygen point because when you plot iron to silicon versus iron to oxygen, it turns out it's highly diagnostic of meteorite compositions. This is a similar kind of measurement that Tom Freeman used to make the first chemical connection between the HEDs and Vesta. So here, and just to overview, these are meteorite compositions from Nittler et al. You can see, it's probably pretty hard to read the label, but I'll just sort of give an overview, which is that there's this dividing line, and everything down here is achondrites. These are HEDs, SMCs, lunar samples. You go further up on the trend line, you have the LL chondrites, the L chondrites, and the H chondrites. Here are the EH and the ELs. And then you have this breakout, which is the carbonaceous chondrites. And here are where the near measurements fell out. Here, Larry Evans et al.'s paper, this was the first analysis of the landed measurements from the near GRS, fell out here. The iron to silicon ratio is not unusual and is consistent with L and LL chondrites, but you see the iron to oxygen is really low, and in the end this value ends up in the achondrite range, which of course is not really what you expect for Eros, and particularly these orange guys are the HEDs. So this was a very unusual result. And then here's the XRS iron to silicon band. They didn't do an iron to oxygen measurement. And you can see nicely bracketing the H chondrites here. So one of the primary motivations of this analysis was to figure out what was going on with these two measurements. And what that starts with is the surface measurements for the BGO outer shield detector for the near gamma ray spectrometer. You can see here a 50-kilometer orbit spectrum. This was far enough from the asteroid that it consists entirely of spacecraft backgrounds. There's no signal from Eros here. And you can see the surface spectrum. And you can see many new features, which are highlighted here by these notes. Many new features appear. But the energy resolution of this detector isn't that great. It was really intended to be the anti-coincidence shield for the inner detector. So most of these signatures overlap. For instance, here's the high energy iron peak, but there are several other peaks, and then the oxygen peak out here. So that complicates the analysis. But that analysis took the form of starting with this spectrum, and from it deriving peak areas. There you do background corrections and corrections for detector efficiency to measure a photon ratio, which is then converted via radiation transport modeling to elemental abundances. So every single one of these steps we have revised since Larry Evans' initial analysis about 13 years ago now. I won't go into details about all their revisions, except just mention one, which was one of the funner sides of the project, in my opinion, which was this detector efficiency. So, of course, when these guys launched this thing, they thought they were going to be making measurements of the asteroid from orbit. So they calibrated the detector efficiency for a very narrow range of viewing geometries, just looking right through the bore sight to the asteroid. Of course, these measurements are on the surface with the GRS practically buried in the regolith. So here you're getting signal from plus or minus about 90 degrees, a completely different measurement orientation than the instrument was calibrated for. So we got a hold of the engineering model. It was collecting dust in the basement of the Smithsonian. We brought it up to APL and did a comprehensive energy-dependent calibration of the detector for the landed geometry. So that's just one example of the improvements we made to the analysis. So as a check of that analysis, including the background corrections, the efficiency, etc., we took a look at silicon to oxygen versus magnesium to oxygen ratios. You can see the light triangles, those are all meteorite types. And then in here, I've shown the L, the LL, and the H, going in with the assumption that Eros is an ordinary chondrite based on what Tim McCoy found. You can see those values are not particularly diagnostic of meteorite type, which is good, because I'm using this as a check. If your analysis is working out right, you expect to get an answer something in this region. You can see, maybe not see, there's a little red cross showing our result. There are big errors. Again, this is due to the background corrections, which were, and the inability to resolve the peaks. But you can see our result lies nicely on this diagnostic measure, providing some confidence that we're on the right track. So then we can start to look at more diagnostic compositions. For example, magnesium to silicon versus iron to silicon. Here's the near result. This ellipse is at 2 sigma statistical plus systematic errors. You can see the achondrite compositions are all out here. Here are the LL, the L, and the H chondrites. The near result is pretty consistent with the L and the LL. There's a little bit of the H that come in. Here are the carbonaceous chondrites, and those sort of straddle the boundary of the measurement. So this is in and of itself doesn't resolve our problems, but if we go to the iron to silicon measurement, or iron to silicon versus iron to oxygen, we finally get into a really diagnostic regime. Again, here was the Evans et al. Result, and here's the result from our new analysis. And really what had happened primarily was one of the corrections we made to the oxygen for backgrounds really pushed this answer up. And you can see it beautifully includes now the LL and the L chondrites. Here are the H chondrites. There are a couple examples where they peek into the error ellipse, but the vast majority of these things fall outside. And then here, again, are the carbonaceous chondrites. Again, a couple of those fall in. Most of them are outside. There are other reasons to rule out carbonaceous chondrites. The spectral data, for example, is completely inconsistent with that, as are most other major elements. So this is finally pointing now towards an L and an LL chondrite composition. We can revisit that. Right. So then that raises the question, what about those XRS results, right? They had a much higher iron to silicon ratio. Well, you can go back about 10 years now. Okada et al. Had an LPSC abstract suggested that the XRS measurements were very sensitive to a phase angle correction. Basically, the viewing geometry had a huge effect on the derived iron to silicon abundance. The most recent analysis of the XRS data, Lucy Lim and Larry Nittler in 2009, they could not find evidence that that was taking place, so they derived the iron to silicon abundance that we've been using as part of this analysis. But it was finally recently with actually messenger XRS data that we were able to confirm that this is indeed a problem. You can see here iron to silicon measurements before and after a phase angle correction. So they're plotted here as a function of phase angle. Here are the messenger iron to silicon measurements as a function of phase angle. There's a clear dependence on phase angle that has to be corrected. And with the XRS data, there was sufficient information to perform an empirical correction, flattening that out. NEAR, unfortunately, that's not the case. There were just 8 measurements taken from 8 different flares during the orbital period with very large error bars. So you cannot correct, at least you cannot empirically correct the NEAR iron to silicon data, making that no longer a valid constraint on Eros' surface composition. So we can go back to that initial table that we had, and we can modify it. We can rule out this iron to silicon abundance, and we can replace the iron to oxygen now with our new finding that it's consistent with the L and the LL chondrites. And now you see a really nice consistent picture, right? Everything is now pointing towards an LL chondrite-like composition. Except this, right? We've got this silicon to sulfur, this subchondritic value. And folks have been thinking about this for a while. And sulfur is moderately volatile, so the initial focus was basically on space weathering, depleting sulfur relative to our measurements for the ordinary chondrites. So then the question is there any additional evidence that this process is occurring? One of the elemental abundances that Evans et al. Reported was potassium. The errors were large, but overall it was consistent with the ordinary chondrites. It did not point towards a depletion of potassium. But are there any other useful volatiles that we can look at in the data? Well, turns out there's one, and that's hydrogen. So we wanted to get at a hydrogen measurement for Eros. Of course, most of the time you do that with a neutron spectrometer, but NEAR was the only mission in this era of discovery missions. We have a lot of times the gamma ray spectrometer and neutron spectrometer are paired. NEAR was the only mission in recent history that didn't do that. It only had the gamma ray spectrometer. So that complicated the derivation of a hydrogen abundance. So we instead applied a pretty novel technique. This was developed by Larry Evans and Steve Squires back in 1987. They were thinking about how to measure small abundances of hydrogen from Mars Observer, which only had a gamma ray spectrometer, didn't have a neutron spectrometer. So they developed this really nice technique to use gamma rays to measure low amounts of hydrogen. They were ready to go, and Mars Observer exploded. Then the replacement, Mars Odyssey, had a neutron spectrometer. So this technique was never applied. We're dusting it off and applying it for the first time. And the way it works is by looking at the photon ratio for iron gamma rays. So it's 2 iron gamma rays, so it's constant, right? The iron isn't changing as this measure, but it's sampling indirectly the neutron flux, because the numerator in our iron photon ratio is generated by neutron inelastic scattering, and that requires high energy neutrons. The denominator is a neutron capture reaction, which is vastly more efficient for low energy neutrons. So this ratio indirectly samples the high to low fluxes of neutrons, and by extension hydrogen. And you can see that here. So for an LL chondrite-like composition, here's that photon ratio. This is from radiation transport modeling, showing that it decreases as a function of hydrogen. Similarly, we have an H chondrite here. You can plot that. It again drops as a function of hydrogen content, but it started out higher. So in other words, if you have an iron photon ratio, say 0.75, that could either be an LL chondrite with around 500 ppm hydrogen, or it could be an H chondrite with around 2,000 ppm hydrogen. So for this technique to work, you have to know something about the surface composition. Luckily, we have now put ourselves in a position where we feel that the surface of Eros does look like an L or an LL chondrite, so we can then apply this technique. So what we've got here is a more complete sampling of that phase space. Here's the iron photon ratio as a function of sigma A. This is the macroscopic neutron absorption cross-section. I don't want to get too much into it. It also influences the neutron flux. You can think of it to first order as being a measure of the metal content. So we took a bunch of different representative samples, starting with lunar hyalins, HEDs, we have SNCs. Here's the LL and the H chondrites, Paul 11, N-site chondrites and CH chondrites. So in general, getting higher and higher metal content. And for each of these test cases, we plotted as a function of hydrogen what happened to this iron content. And you can see this iron photon ratio. And you can see that we went from 10 ppm to 0.3 weight percent. For each case, the photon ratio drops. That's exactly what we saw in the previous plot when we were just looking at the two. In each case, they drop and they trace out these contours. So the blue, they sort of look blue here. The blue lines are contours of constant hydrogen, and the black lines are contours of constant composition. So then we can ask ourselves, well, where does the near result plot out? It's right there. Here's the near value. Here's, again, the 2 sigma uncertainties. The value right here plots very nicely to about 750 ppm hydrogen, although, of course, there's a pretty wide range here. Allowed values go from 250 to 1,500 parts per million. So how does that compare to what our expectations might be? Well, meteorite falls. So the fall is, when you saw the meteorite come down and you pick it up as quickly as you can. So they're the least likely to be contaminated by terrestrial volatiles, although not entirely. But you can see for LL chondrites, you get a mean value of 790 plus or minus this huge standard deviation of 760 ppm, and something similar, a little bit lower for the LL chondrites. So wide range of values here, but importantly, all consistent with our with what we found for Eros. Again, a mean value of 750, and much, much higher than what you see in the lunar hyalins. So lunar hyalins values go from, well, that got kind of cut out of the box here, but from about 4 ppm to 150 ppm. That's from lunar samples and from global mapping from Lunar Prospector. So this as a stand-in for just a surface that starts out hydrogen poor and is exposed to solar wind implantation, clearly what we're seeing with Eros, it's much higher than that. So there's probably some endogenous hydrogen component that we're measuring, and it looks just like it does for the meteorites. So in summary, what have we learned? We've learned with a little bit of reanalysis, we've found that we can now say that the surface composition of Eros is exclusively consistent with the L and the LL chondrites. So we went from that whole ordinary chondrite box, and we got to throw out the H chondrites. I was hoping to get it down to 1, but that wasn't the way the data worked out, and it is what it is. But we're just down to L and LL, and all of these data sets are now consistent with that. We also found that the surface of Eros has a hydrogen content of 250 to 1,500 ppm. So overall, there really isn't any evidence for hydrogen depletion, just like there wasn't any evidence for potassium depletion. So the XRS sulfur depletion measurement kind of stands out now and is interesting, and we have to think a little bit about those space weathering mechanisms and whether or not there are mechanisms that would just remove sulfur, not these others. And then I didn't talk too much about this. I did mention the landing in a pond. One of the theories for pond formation is electrostatic levitation, filling in these topographic lows. The idea that this would occur electrostatically has thought maybe that would fractionate metals from silicates, but now that the XRS global measurements and our measurements landed at that single pond are in agreement, there really isn't any evidence for a process that fractionates these two. It doesn't mean it's not happening, but there's nothing to support that in the data. So that's what we found, and I think it's really exciting. We're starting to wrap up an old analysis here with NEAR, especially as we're thinking about all these new asteroid missions. So I'd love to take any questions you guys have.
Thank you, Patrick. Any questions, please?
Oh, it's really interesting. Mark Robinson on ASU. I don't know if Gene Heiler was involved in this work or not, but we had originally written a proposal to do something along those lines in 2001, and we were told by LDOT, no, you cannot do that because it's engineering and it's not science, and you should have paid for it with mission money, but the mission was ordered not to do any analysis of the data with a 2-week extension, so it's kind of a funny catch-22. It's just awesome you're doing this. That's a really great result because the whole idea that the ponds and the sorting took place was kind of really too convenient and pat because it works so well. But now you've made it more complicated, and maybe you're proving the ponds don't exist because they have no compositional difference, and yet they have they're the only thing on the asteroid that really has a color difference relative to the rest of the asteroid. So maybe what you've shown is that we didn't actually land on the pond. Maybe we landed off to the side of it on the average stuff and not the pond.
Well, that's an interesting point. I guess it was, I know, I can't think of his name right now, had actually revisited the landing site imagery and found that the landing site that was reported by Bavarica was wrong by 200 meters, which doesn't sound like much except it's a pretty small body. So in the end, though, the thought that it landed in a pond is still consistent in that that's what you see with the last imagery. Of course, you might have landed on the edge. And the idea...
But the last image was taken before it landed, so it was still moving.
But now we've got some trajectory, and it looks like it's still headed for this pond. I think it's still consistent with it. I can touch base with you later about some of this new landing.
Yeah, I'd love to hear that. So, but why is the pond blue then?
Well, then that comes to the other answers, which I think you were the ones who suggested some of these hypotheses. For instance, different grain size. So if there's just different grain size filling these ponds, they would look bluer, but they wouldn't have any compositional difference, which is consistent with what we're seeing here. So personally, I would kind of favor those explanations, but I don't know enough to weigh in.
But you're still certain we landed on a pond.
It looks that way, yeah. Yes. I think we still did.
Cool.
Well, thank you again, Patrick.